imagine the handle of the door is here. And the pivot point, and we're going to start talking about vocabulary here. So all the vocabulary I'm going to use today, I will highlight when I think it's a vocabulary word, but some of it is phrases. So the pivot point, I'll use a small triangle to indicate the pivot point, also known as a fulcrum, is at one edge of the door. That represents the point about which the door can rotate. I think the bulb in my projector is starting to dim, so I'm probably going to be dimming the lights more frequently so you can see the board easier, okay? If that causes you to fall asleep, well, enjoy your rest, but the moment you do, you understand that you're fair game for the rest of us. Okay, as long as we have an understanding, I like to make sure I have a little bit of consent before we, make fun of you while you're asleep, because we will. So, the door has the capacity to have a upwards or a downwards rotational direction. Does that make sense? But we're looking at it for up and down. So when the door swings open this direction, the direction of rotation is into the board. Do you follow what I'm saying? Because if I use the right-hand rule, it rotates this way, my thumb points into the board. So my direction of rotation would be into the board. How do we express into the board as a vector? And when the door closes, it's in the other direction. That's going to be out of the board. We probably need some symbology to handle vectors that are into our paper or out of our paper. And luckily for you, we don't have to come up with that symbology. It already exists. So into the board and out of the board is represented by a circle with a dot and a circle with an X. This represents out of page or out of board, and this represents into board or into page. I guess I should be consistent, so I'll say into page. The idea is that, remember, a vector is an arrow, right? When we've drawn vectors before, we've drawn them as arrows. So if this were an arrow, like a physical arrow you would shoot, if the arrow were coming at you, you would see the point, thus out of page is just a dot. And if the arrow is going away from you, you would see the fletching or the feathers, thus you see the X. Does that make sense? So that's what the symbology represents. So if I go to open the door, then I would say that there is a direction of rotation, and I put the X there to indicate that it's got a vector of rotation into the page or into the board. Does that make sense to all of you? Okay. It is quite plausible that on an AP exam, they will use this symbols. It's less plausible in this class that you will have to draw these symbols. E&M, you probably would, but in this class, you probably wouldn't. But they might do something like this. The idea here is they are stating the directions that they call positive by drawing a 3-axis symbol on your paper, and they're establishing up is positive, X is positive, and out of the page is positive. That's not an uncommon thing to see on a diagram on an AP exam. Everybody follow along? It's just a way that they will establish it. They may be nice enough to put little positives there, but they are probably more likely to explain it in the diagram or the dialogue of the problem. So just be prepared to understand out of the board is a dot and into the board is an X. All right. We determined yesterday that if we want to open the door, we will have to apply a force to the door. And to do so, we have choices about where we could apply that force. We could apply the force further away from the point of rotation, and we know that that makes it easier to open the door, and that the closer we get to the point of rotation, the more difficult it is for us to open the door. So the understanding here is that our applied torque is dependent upon where we apply the force, that it is dependent on that value, but it's also dependent on how much force we apply. If I want to increase how hard I turn the door, I can do so by increasing the size of the force I apply. But I know that it's also affected by moving that force to a different location. As Sam found out, you can just grab the edge of that door and whip it closed, maybe not applying even that much force. Now, I bring this up because what we didn't talk about yesterday, and I probably should, is that what if instead of applying the force the way I did, I try to close or open the door by applying the force like this? Would this be an effective way of opening or closing the door? I don't think it'd be very effective. You guys see that it probably would not? Does it make sense that the only way the door opens or closes is if there's a component of this force that is perpendicular to the door? Like if I take this force and just turn it a small amount, the door might open. This might not be the most effective way to open the door, but it might, because at least a part of that force is pushing perpendicular to the door. Does everybody understand this so far? Because torque's a little more complicated than what we might just say you push someplace on the door. It involves this angle, and it's got several names. Angle of attack is one of them. I won't use that phrase because it's not really on the exam. It's kind of falling out of favor. But it's just the angle of application of your force. Now, just to be clear, we need a way of measuring this angle, and you have several choices on the way to measure this angle. One of them is to measure that angle relative to the perpendicular, and one of them is to measure it relative to, say, the door. We don't use either of those. The angle that is used is the angle that is related to the torque arm. The torque arm is a second vector, and the torque arm vector is a vector that starts at the pivot point and stretches to where the force is applied. We call this the torque arm. And it is a vector, and we will use lowercase r to represent the torque arm. Again, it's from the pivot point to where the force is applied. Again, we call this the torque arm. Obviously, this arrow is our force. The angle that we use is the angle between the torque arm and our force. Now, in trying to define torque, again, lowercase tau, obviously it's going to use the torque arm value and it's going to use the force. Hopefully you recognize from our conversation that if you increase the torque arm, you increase the force. You increase the torque arm, you increase the torque. And if you increase the force, you increase the torque. There's only a number of ways you can put variables together to make that happen. In torque, it's a product. So you multiply the size of the torque arm and the size of the force to get the size of the torque. So doubling the torque arm doubles the torque. Doubling the force doubles the torque. But the angle is also involved. How do you think the angle's involved? You can probably imagine it's trig. So which trig function do you think would work best here? Which one would give us a maximum when that angle is 90 degrees and a minimum when that angle is, say, 180? Sine. Yeah, we use sine for this. And because of the way sine works, meaning that it's positive in both the first and second quadrant, you can actually use either of these two angles. Either will work because they're supplements of each other, and the sine of the supplement is the same value. So it doesn't matter which one of these two you use. I'm bringing this up because you're going to have to identify torques in diagrams, and they will often try to trick you and say they're measuring it from here. That's not how torque is calculated, and that's not the angle that we use. So keep in mind, the angle that is built into torque is the angle between the torque arm and the direction of the force. And it's a maximum at 90 degrees. Now, keep in mind, torque arm and force are vectors. So what we've written here is actually the magnitude of the torque. This gives you how big the torque is. It doesn't give you the direction of torque because torque is a vector. So to write this as a vector formula, we actually write it like this. Most of you haven't seen this unless you've been in E&M, but this is called the cross product. It's a way of multiplying together two vectors that will give you a vector. You've seen vector products before. We had a vector product earlier in the year. Does anybody remember the vector product from earlier in the year? The dot product. Thank you. I couldn't get that out of first period. It's nice to know that one of you remembers. The dot product. Writing it without calculus, the dot product looked like this. The dot product was also called the scalar product. It produced a scalar from two vectors. It told us how much one vector was in the same direction as the other. So if you remember, the magnitude of this vector involved the cosine, because we used the cosine of the angle between the force and the displacement, because that told us how much of the force was in the direction of motion. This gave you a maximum at 0 degrees and a 0 at 90 degrees, because that means if your force is perpendicular to the displacement, it does no useful work. That was the whole point of talking about work. Torque is different. It's a vector product. And the idea here is that it's most effective at 90 degrees. And so our value is based on the sine of that angle. And that gives us our magnitude. But it doesn't give us direction. For direction, we need the right-hand rule. So I want to talk about how and why it's written this way, but also let me talk about one more quick little thing. When we calculated work, our units here were newtons times meters times the unit of cosine, which is unitless. So this gave us Newton meter, and the Newton meter is a joule. Right, this is a unit of energy. If you're paying really close attention, you should recognize that this will give us meters times newtons, which looks to be the same units, because if I use the commutative property, I can multiply in any order. Shouldn't this still be a Newton meter? And the answer is no. Torque specifically does not have another unit to replace it. It's written meter Newton on purpose to let you know this is the unit for torque and is not a unit for energy. The meter Newton is the standard unit for applying a torque. The other version that maybe some of you know about because you've worked on like equipment and things, the foot-pound. So foot-pounds of torque. If you are into cars, you know that cars will talk about their torque values based on how much torque the engine can provide. That's how hard the engine can twist. And so you can look at the torque curve of an engine. Also, how many of you have used a torque wrench before? Oh, excellent. So some of you have used a torque wrench. You understand a torque wrench either has a gauge on it that tells you the amount of torque you're applying, has a needle on it that tells you the amount of torque you're applying, or is set at a specific torque value and gives you an indicator when you've reached that torque. That's the kind I have. So when I take my bike apart today because I blew a tire on Tuesday, I will take the whole thing apart, but when I put it back together, I follow the guides for all the torque values using a torque wrench. It tells me how many, my bike's meter newtons, so it tells me how many meter newtons for everything. But foot-pound is another version of torque. It just tells you how hard you're twisting something. You don't want to over-torque a bolt because you can break it. So let's handle the direction of torque now. We're using the fact that the middle of the meter stick, pretty close, was where our center of mass was acting. So this is the mass of the meter stick, or the weight of the meter stick. I have a fulcrum, which is a string pulling upwards, and this is at 30 centimeters. This is at 50 centimeters. And then I placed a 100-gram weight at 14.4 centimeters. And again, this was a 100-gram weight, so 0.1 kilograms and 10 meters per second squared. And try as I might, we were trying to bring the system into static equilibrium. Some of you who looked up different kinds of degrees who found that in certain engineering degrees, you have to take a class called statics. You probably saw it on there. Statics is what we're seeing here is the introduction to statics. Statics isn't just Newton's first law. It's Newton's first law for systems that are at rest. But now we're talking about not just force, we're talking about force and torque. So a statics problem is one in which our system has a net force and a net torque of 0. So our system is not moving or rotating. Now there were 3 forces acting on the meter stick. The weight, the applied 100 grams, and what other force? Well, that was the weight. Tension, that's right, tension. 3 forces acted on our system. Tension doesn't cause a torque because tension is acting at the pivot point. And any force that acts at the pivot point doesn't cause a torque. But there was the torque from the applied weight and the torque from the meter stick, and they have to sum to be 0 for the system to be in equilibrium. We'll finish this tomorrow.